Okay, I think we're good. So section 2.01, like I said, is rates of change and limits. The first thing we're going to investigate here a little bit is the rate of change side of things, and we're going to look at average speed versus instantaneous speed. So if you guys have had any physics in the past talking about motion and that sort of thing, you've probably dealt with this, even those that haven't have probably seen this in a science class at some point. So let's say that I've got, well, before I get to an example, let's just talk about this for a second. Average speed. What do you suppose that is when I'm talking about an average speed of something? What do you remember about that? Okay. So it's the change in distance over a change in time. A speed is really a ratio, right? Think about the units that we use for speed. Miles per hour, meters per second, that sort of thing, okay? It's a measure of distance or a change in a distance over a change in time. Okay, so let's say that I've got an equation for my distance that is 16t squared. Okay, so when objects are in free fall, this equation might look familiar, but when objects are in free fall, they tend to follow this kind of an equation, 16t squared. So we're going to use that, and let's say, and this is, so this is measuring the distance an object has fallen after t seconds. So then my question for you is, bless you, what is the average speed of an object during the first 2 seconds? Okay, so remember, the variables in this equation here, y is measuring the distance, and t is measuring the time. So if average speed is the change in the distance divided by the change in the time, how can I do this then? How can I answer that question? Okay, so plug in a 2 for t. So y equals 16 times 2 squared. And that's going to get me 16 times 4, which is 64. Okay, so by plugging in a 2 into this equation, remember the equation is measuring the distance an object has fallen after that many seconds. So after 2 seconds, the object has gone 64, I don't know, feet or whatever it is. I don't know what the measurement is for this one, or what the unit is for this one. But it's gone a distance of 64. Okay, so how can I use that then to calculate my average speed for this object? Divided by 2. Because the change in the distance is 64, the change in time would be 2, right? That's over that first 2 seconds. So, let's see if I got some room here. So the change in distance is 64. We know the change in time is 2. Now I want to caution you a little bit here because this particular equation, the distance and the time both start at 0, right? When t is 0, then the distance is 0, according to this equation, okay? What if the equation I had been using was like 16t squared plus 5? What would be the starting distance? 5. So then what would be the change? Exactly. Whatever you get when you plug in your number, then minus 5. So you got to be careful, okay? It's not just plug the number in and go. Remember, it's a change. So where are you starting, where are you ending? This is from 0 to 2, and 0 gets us 0, so we don't have to do that. But remember, you're doing a change each time. So in any event, our average speed here then, 64 divided by 2, so that's going to be 32. And let's say we were measuring this in feet, so this would be 32 feet per second is our average. All right, great. I think you guys are all okay with that. Now, what if I wasn't concerned about an average over a certain interval? Because we had to do this over an interval, right? From 0 to 2, what was the average speed that it was traveling in that interval? What if I wanted to know, okay, right exactly at 2 seconds, how fast is it going? I'm not concerned about an average. I'm not talking about an interval. I'm talking about at one instant in time, how quickly is that object moving? Okay? And that's going to require an instantaneous speed calculation. Okay, so instantaneous speed. Well, to calculate speed, I got to do this whole change in distance divided by change in time. Well, if I've got 1 instant in time, then I don't really have a change that I can measure for either one, right? So if it's 1 instant in time, what is the change in time technically? 0. You ever see the problem with that? What happens when we're trying to calculate this change in distance over change in time then? Can't do it, right? You can't divide by 0. That's like one of the first big rules in math we talk about in high school. You can't divide by 0. So if we're doing an instantaneous, it seems like it's impossible. And in fact, for centuries, mathematicians thought it was impossible to calculate because of that fact. You got to divide by the change, and if there's no change, then you're dividing by 0, and you can't do it. But there's kind of a workaround that you can do. Let's say that my time, let's do so I'm going to do time t and t plus h. And this h is going to be some tiny increase in time. So if we make it like super duper small, like 0.0001 or something, okay? So yeah, technically it's still an average, but it's really, really close. So we can think, oh, it's got to be pretty close to the answer there then, okay? And there's a little bit of a workaround with that then. So if we've got these two, let's try that same thing again then. So let's see if we can answer the question, what is the instantaneous speed at t equals 2 seconds? Okay. So this whole change in distance over change in time, what is this going to look like now? Okay, well think about what we did. When we found the change in distance, basically we were finding the difference of the y values, right? So it's kind of like doing a slope, essentially. Change in the y over change in the x. Or instead of y, it could be f of and f of. So this is going to be f of t plus h minus f of t. That's the change in the distance. We have to take the t plus h and the t, plug them both in and find the difference. And then over t plus h minus t, if those are the two time values we're going to use. And in this case, because we want to find it right at 2 seconds, the t is going to be 2. So we're going to just take the t's and make them all 2's.
It's supposed to be excused, but I guess my mom didn't call yet, so
Okay.
she's going to change it.
All right. Okay, so that's where I'm at right now in doing this calculation. And the denominator, 2 plus h minus 2, that simplifies, right? What do we actually have in our denominator then? H. Okay. So f of 2 plus h minus f of 2 divided by h. Okay. So here's the thing. For h, for this thing to technically be instantaneous, what does h need to be if h is this little tiny increase after t? Right now we're kind of like approximating it because I said, make it like 0.001. It's like this teeny tiny little increase in t. But what do we really want h to be? 0, right? And again, right now, if I were to make h 0, that's a problem, right? Because then I'm dividing by 0 and I can't do that. Okay? So what we're going to do is instead of doing this as directly and making h 0, which would give us something we can't get, we're going to think about it in terms of a limit. So we want h to move towards being 0 instead of jumping right there. So we're going to do this. The limit as h approaches 0 of this. And so we're going to go back to our equation, plug this stuff in, right? We still got to do this f of 2 plus h and this f of 2. Plug those back into that original equation, that y equals 16t squared, and kind of see where I'm at. Okay? So this then is going to get us the limit as h goes to 0. F of 2 plus h would be 16 times 2 plus h squared. And then f of 2, that we already did earlier, right? That was 64. So we're looking like that now. Okay, when you plug the 2 plus h in, you get 16, 2 plus h squared. When you plug in a 2, you get 64. So we're there. So now we can simplify this. We've got to square out that 2 plus h. FOIL that thing out. See what we get from that. So we end up with 16 times 4 plus 4h plus h squared minus 64 divided by h. And then if we do a little distributing there, get the limit as h goes to 0 of 64 plus 64h plus h squared minus 64 all divided by h. Oh, 16h squared. You're right. Yep. Thank you. Yeah, I got to distribute that 16 to all three of them. Okay, so there's a couple things that are going to happen now algebraically. If you look at this thing, what's the first thing that's going to happen? Yeah, those 64s can cancel. And now look at it. If those 64s are gone, you're just left with this in the middle, right? Something else that can happen then. You can factor, and then after factoring even, what can you do? Yeah. This 16 right here? This? From the equation. It's 16t squared. So I did 16t squared. Because our t was 2 plus h. So what's going to happen in that middle there? Yeah, we can factor that, but more than that, though, yeah, that h can go away now. We can cancel that out. So if the h's are gone, and these 64s are gone, we've got the limit as h goes to 0 of 64 plus 16h. Okay, that's doing both those cancellations there. So take a look at what we have now. Remember before we wanted h to be 0, right? You said if h is 0, then we got what we want. That's the instantaneous rate of change, right? And we couldn't do it up to this point because we'd divide by h, and that's bad. Or we divide by 0, and that's bad. But now that we've canceled the h using our algebra, we got something we can use, right? Plug in the 0. What's the instantaneous rate of change here? It's 64. That's the answer. It's not an approximation. That's exactly what it is at 2 seconds. 64. Okay, so we are capable of figuring out how quickly something is moving at an instant by using this rate of change idea. Okay, this is what we just did right here is called the difference quotient. You might hear that lingo later on, but that's what this is called when we do this instantaneous work like we just did here with the h's. It's a difference quotient. But it allows us, because every single time you do one of these, you should end up in a spot where the h will cancel, and then you can plug in, and then you've got an answer. Okay, so this allows us to get at instantaneous rates of change. And later on, we're going to look at derivatives, and what derivatives do is streamlines this process for you. So you don't have to sit here and write out all these limits every single time and go through all of that garblegook to get to the answer. You can just do like a two-step boom, boom, got it type of a thing. But that's essentially what a derivative measures, though. A derivative is an instantaneous rate of change measurement. Okay, that's its definition. So we're going to get to that later, but for right now in Chapter 2, like I said, we're going to focus on the limit stuff and work with that a little bit more. So I really wish I could have you guys practice this a little bit more, but I got to move on. So, but we will get some time to practice that a little bit more later. So since we need to use limits to do these calculations, we had that limit as h goes to 0 part of that thing that was how we got through that. It's worthwhile to just talk about limits in general here for the rest of the time. Make sure that we're okay with how we do those kind of types of calculations. So we're going to jot down a few things that we know about limits, and then work on a few practice problems involving them. So what a limit is, so it is a value that a function approaches as x approaches a value. Okay, so when I say a value that the function approaches, what kind of value is this? Well, it's a y value. So what happens to y as x approaches something else? Okay, and some of the easier ones to look at are if you have a graph in front of you. So that's what we're going to do first. We're going to take a look at doing limits on a graph. So let's start with that graph. See if you can answer some limit questions for me. So what is the limit of f of x as x approaches infinity? What is the y value that it's getting closer and closer to as x goes to infinity? What was it? 0, yeah. Okay. Now we're going to talk a little bit about these guys some more later, but I might as well talk about it now that since we got one in front of us we can use it for. I'm going to zoom in on this a little bit for you. This next one, see I put that little negative up there by the 0, kind of like an exponent? That means from the left. Okay, so what is the limit of f of x as x approaches 0 from the left side? Where's it going? To infinity. Yep. And then likewise, what is the limit as x approaches 0 from the right? So I put a little plus sign up on that 0 there, and that means from the right side. Yep. Negative infinity. Okay. So that's kind of the idea looking at a graph. Now, they might give you some other ones that are like so easy they're hard or so hard they're easy. I don't know. Where it seems more difficult than it actually is. But maybe not. I don't know. So let's say we've got a piecewise defined function here that looks something kind of like that. So this is at 1, this is at 2, this is at 3, 1, 2. Okay, so something kind of like that. And I'm going to do the same thing. I'm going to ask you some limit questions next to that one and see if you guys can answer them for me. So what is the limit of f of x as x approaches 1? So as x gets closer and closer to 1, what does the value of y get closer and closer to? 2. Nope. 3. I think maybe you did -1. But as we get closer to an x value of 1, or maybe you're doing this one instead, yeah. As we get closer to an x value of 1, where's the y value? Up at 3, right? So this is equal to 3. Okay, so what is the limit as x approaches -1 of that function then? So as x gets closer to -1, y is getting closer to what? That one's 0. Okay, what about that one? What's the limit as x approaches 0 of f of x? From the left, it's 1. What if I went from the right? That one, well, it doesn't actually get to 2, but it approaches it, right? So this particular one, if I had made this like a little from the left with the negative on it, then the answer would be 1. And if I made it from the right with a little plus next to it, that answer would be 2. So what do I do with this then? What is the limit as x approaches 0 then? Well, it doesn't exist. Because it depends on which side I'm coming from, right? All the rest of these, the limits from either side approach the same thing. Like for 1, it doesn't matter which way I approach it, right? Both of them are coming up to 3. -1, doesn't matter which direction I approach it from, both of them are coming together at 0. But this one, as I approach 0 from either side, I'm going to 2 different places. And that limit can't exist then if it's coming from 2 different places. So we would just write DNE, does not exist for that one. Now, like I said, though, that being said, if I had done, like, let's say the limit as x approaches 0, let's go from the right. It's called a right-hand limit. So what is the answer to that one then? Like I said before. Approaching 0 from the right, it's 2. Yeah, it's approaching 2. So that still exists. It's just the limit by itself approaching 0 can't exist, though, because you can't have 2 values for the same thing, for the same limit. Okay. So even if there is a hole in a function, if there's a space missing or something like that, the limit still exists, but the value of the function does not. And this is something that a lot of students in the past have struggled with a little bit. So I want to make sure that I kind of hit it a little harder this time. So let's say we've got this function. It's got a removable discontinuity in the middle of it. It's like somebody just shot a hole in it. And it's defined for every x except for, let's say, 1. And this is 1 up there as well. And let's make this a 2. Sorry. Using 2 different numbers will be easier to see what's going on. So let's say that's 2. Okay. So the limit of this function as x approaches 2 is what? It does, actually. It would be 1. Now, if I asked you what is f of 2, what's that? What's the value of x, or what's the value of y if I plug in a 2? Well, there's nothing there, right? So does this have an answer? No. Does not exist. Can't do it. Undefined, however you want to say it. Okay, the limit exists, but the value of the function there doesn't. Okay, because a limit measures what are you approaching, not what is it exactly at that spot. Okay, and that's an important distinction between these two things. Okay, so think about it. I always talked about approaching from either side. Okay, the limit as x approaches 2. So as I approach 2 from either side of this thing, what value am I approaching? 1. Am I ever really getting there? No. But am I approaching it? Yes. So the limit does exist. The limit is equal to 1. The value of the function doesn't exist there. Okay? That's the difference between a limit and actually evaluating a function. Because sometimes once we get into these limit calculations a little further, students start to kind of slip back into, oh yeah, you're just plugging numbers in, and it's just like plugging a number into a function. Well, not always. It depends. Okay, a limit measures you approaching something, not actually being there. So it's a little different. So, that being said, we're going to take a look at some doing limit calculations with equations. And there are some different techniques we're going to talk about with this. The first thing you always try and look for when you're trying to do a limit with an equation is, can I just plug it in? You always hope for those. Those are called substitution limits. Okay, so that's kind of like, because you're going to kind of go through this progression. Check for this, check for that, check for that, check for that. So substitution is the first thing you want to check for. Can I just plug the number in? So example of a substitution limit. So if we had like the limit as x approaches 2 of x plus 5 over x minus 3. Okay. So put in a 2 and see what happens. Okay. So 2 plus 5 over 2 minus 3. So that's 7 over negative 1, so negative 7. The answer to that limit is negative 7. Done. So check to see, can it be plugged in? Now, if it can't be plugged in, then you might have to go to doing something else to get there. Okay, we have some limit properties we're going to talk about, but before that, you might have to try to simplify what you have. And when we did all of that rate of change business with limits, this is what we were doing. This is the stage we were at, was trying to simplify. So, to give you an example, so let's say we got the limit as x approaches, how about 4 this time? All right, so if I try to go with this one, doing a substitution, immediately you can see the problem with that, right? What's going to happen if I try to do this one like a substitution limit? You're dividing by 0 again, which is bad. So what we're hoping for then is, can we factor some things out, do some cancellations, so that this x minus 4 just goes away? And then we can take whatever's left over and plug in and use that then. Okay? So x squared minus 6x plus 8. You guys factor that for me here. What are our two factors for that? There you go. Yeah. So x minus 2 and x minus 4. And then the x minus 4s will cancel. Yep. And so we'll be left with the limit as x approaches 4 of x minus 2. So what we've done is we've done some simplifying to turn it into a substitution limit, because now I can plug in, it's not a problem. 4 minus 2, that's 2. So the answer to that limit should be 2. So substitution, try to simplify. Those are kind of your first two things that you're going to check. If those two things don't work out, you might need to use a limit property. So I'm not going to write all of these down, but we're going to kind of skim through them in your book a little bit so you can at least take a look at them. And then I'll show you how you can use a limit property to get at a limit. Okay, so number 3, use a limit property of some sort. So here's what we got for that. This is on page 61 if you're interested in your textbook. But these are some of the properties that we have. So, and all of this are things that we've looked at in different contexts, not with limits, but each of these I think should make a little bit of sense to you. Okay? So, at the beginning it says, the limit as x approaches some number c of f of x, let's assume that that's equal to some number we know and it's L. And the limit as x approaches c of some other function g of x, let's assume we can calculate that and that comes out to m. So the rules go like this then. If you want to do the limit as x goes to c of these two functions added together, then the answer is going to be their two answers added together. Does that make sense? And if you subtract, you subtract. Okay, take their answers and subtract them. If you multiply, you multiply them. If you take one limit and multiply the function in the limit by a constant, then it's the answer to that limit, whatever it was, L in this case, multiplied by that constant. Okay? So like if I know the answer to the limit of x squared at some value, I can do 2x squared just as easily. I can just take the answer to the first one and multiply it by 2. Whatever that number is you're multiplying, and the outside of that, you can just multiply that to the answer, and then you can get your answer that way. Quotient rule, if you divide the two functions, you can divide the two answers, assuming that this one doesn't come out to 0, that m is not equal to 0, because then you've got that same issue of dividing by 0, and then it's a limit you wouldn't be able to do anyway. Okay? So that's why they put this little m not equal to 0 part at the end. Okay? So we've got all of those properties. Let's see. And then there's a power rule. This is at the top of the next page here. And the power rule says, if r and s are integers, so if it's raised to some power and s is not equal to 0, because then you'd be dividing by 0 in this little fraction up here, it is the answer to the limit raised to that same power. So basically with all of these, it's saying if you're doing some kind of an operation inside of a limit, you can just take the answers to those limits and do that same operation to them, and the answer should still be the same. Okay? So, using some of these properties then, see how we can get that to work for us. So what I'm going to do, to really show you a good utility with this, I'm going to show you a limit that at this point you're not going to be able to calculate, but we're going to use it for our purposes here. So, and this is a limit, whoops, I put X in there. This is a limit that you will have memorized at some point because we're actually going to use it quite a bit. But, and I'll show you why this is in a little bit, but the limit as x approaches 0 of sine x over x, do you see why you can't do a substitution for that one? Because it would give you divide by 0 again, right? And do you see how we can't simplify that one? There's no way to factor sine x. We can't cancel anything. We're kind of stuck, right? Okay. The limit does have an answer. And like I said, later on I can show you how we can get that, but it's equal to 1. The limit as x goes to 0 of sine x divided by x is equal to 1. Okay. So knowing that fact, let's see if we can calculate the limit as x goes to 0 of 2x plus 3 sine x over x. So I'm going to use some of those limit properties by taking this limit and breaking it into several limits. and then taking each one of those limits one at a time and calculating them and then getting an answer from that. Okay? So it's really going to just involve a little bit of algebra to get it set up the way that we'll be able to do it. Okay? So the first thing I'm going to do is I'm going to distribute this x so that I've got that to begin with. Okay? So I'm doing the limit of all of that now. 2x over x plus 3 sine x over x. And that first fraction, we can cancel out the x's then, right? We can do a little simplification job on that one. So we end up with the limit as x goes to 0 of 2. And then I'm going to use one of my limit properties and say, okay, if I'm doing the limit of two things added together, that sum rule said that I can break that into two limits. Do the limit of the first one and the limit of the second one. So I'm going to make this another limit as x approaches 0 of 3 sine x over x. Okay, so I've used that sum property to break that up. And then I'm going to use one more property. There's that constant multiple rule that said if I've got something that's multiplied by a constant, in this case this sine x over x technically is getting multiplied by 3, right? So I can take that constant multiple and put it out in front of the limit then. I can get the value of the limit and then multiply by 3, and it's the same thing. So my whole equation here now is going to look like this. And now I have the means to actually calculate that. What is the limit as x approaches 0 of 2? If it's helpful, think about what that function looks like. It's just a straight line at 2, right? So it should be 2. It's always 2. There's no x to plug into. It's just 2. Okay? And then I have 3 times the limit as x goes to 0 of sine x over x. What is this? That's equal to 1, right? So 3 times 1. 3. And then 2 plus 3. The answer to this limit is 5. Okay, so that's how we can use some of those properties to help us out. If you have a known limit, like this sine x over x one that I told you, then we can use some of those properties to take one that looks on the outset like it's impossible. Like, I can't simplify that. There's a sign in the mix there. I can't cancel anything. I don't know how to do this. But if I start to break it apart using my properties, then I've got two very doable limits, knowing this fact up here that we started with. And then I can use that to get my way through the whole thing. Okay, so let's take a look at this one. Calculator. Just so we can kind of visually see this thing as well. We should see a function that is approaching 5 at 0. So we're going to go back and put in the original problem I gave you guys to work on here into your y equals. So that should be in parentheses 2x plus 3 sine x all divided by x. So something kind of like that. Double check that your mode is in radians. Mine's not. Oops. Should be in radians. And your window, maybe let's go to like 8 in every direction. We know the limit's equal to 5, so we want to make sure 5 is in there so we can see it. All right, so if we graph this thing, when x is 0, the function should be approaching 5. All right, so does it appear as though the function is at 5 when x is 0? Yep. Is the function actually equal to 5 when x is 0? Look at the original equation we used. Can I plug in a 0? So does the function have a value at 0? No. If I can't plug the number in the original equation, then the function itself does not have a value there. Now, why the heck did the calculator graph it like this then? Because the calculator works in teeny tiny little pixels. Okay? There's actually a hole right here that you can't see. Right at the top of that hill. It's got a removable discontinuity right at the top of the hill. Okay? So as you approach 0 from either side, you're approaching the value of 5. But if you try to actually plug in a number there, if you actually try to plug in a 0, I can even do that. Calculate value x equals 0, and my calculator's even going to tell me nothing there. X equals 0, y equals nothingness, which means undefined. Okay? So there's nothing there, but the limit does exist because from either side it is approaching that value of 5. Okay? So we have verified that graphically now. That, yeah, that's right. That limit should be 5. Okay. Last thing I want to talk about today is something called the sandwich theorem, and this would be kind of your fourth thing that you want to check here for with limits. All right, and so the sandwich theorem says this. Let's say I've got some function f of x heading along there, and I want to know what's the limit of that function at c, right there. So what's that limit right at that spot? And let's say for whatever reason I cannot calculate it by hand. But I am aware of this other function, g of x, that is always above this function up here. And I'm aware of this other function, call it h of x, I guess, that is always below f of x. Like that. So, if g of x is always greater than f of x, and h of x is always less than f of x, and the limit as x approaches c of g of x and h of x is the same thing, then f of x has to be that as well. Because g of x and h of x have sandwiched that value at that spot. Does that make sense? This one always has to be on top, this one always has to be on the bottom. And at this particular value, if those two are the same, then f of x has to be the same too, because it has to be in between those. So it has to be that exact same thing as well. It is very rare that you run into a situation where this is actually going to work out. Now, there are some specific ones we're going to look at. And you'll kind of, after a while, know them when you see them. Like, oh, that's a sandwich theorem one. Or the directions will simply state, use the sandwich theorem to determine this limit. Okay? So that's kind of the visual of what's going on. As far as what it says, specifically, if g of x is greater than or equal to f of x and h of x is less than or equal to f of x, for all x not equal to c, then if the limit as x approaches c of g of x equals the limit as x approaches c of h of x, and that's equal to some value, we'll call it L. Then the limit as x approaches c of f of x also equals L. Okay, so let's use it once. Show you how it works. Whoopsie. Alright. This will be where we finish up today. So let's find the limit as x approaches 0 of x squared sine of 1 over x. Okay, so we're looking at one where, like the other methods won't work, right? If you try and do a substitution, can't do it because you can't divide by 0 again, right? Because it's the sine of 1 over x. If you try to do, what was the next one? Simplifying, you can't simplify x squared sine 1 over x. There's nothing to simplify. Properties aren't going to help you. There's no properties that we can use to break this up at all that are going to allow us to do it. So we're on to our sandwich theorem line of defense here now. So first thing we need to do is, if this is our f of x, we need to come up with two functions, one of which that's always above this and one of which that's always below this. And that seems like a pretty tall order. Like how in the world am I'm just going to randomly pick two functions that work, that one's always bigger, one's always smaller? Well, yes and no. The fact that there's a sign in this thing helps get started. Sine of 1 over x. We're going to ignore the x squared for right now, okay? But any trig function, as long as you're not multiplying it by something, every single trig function, sine and cosine, are caught between two numbers. Now think y values now, right? What y values are sine and cosine always in between? If there's no change in amplitude, just a regular old sine wave. -1 and 1, right? So I've already got this much of it sandwiched. So your sandwich theorem problems are almost always going to have a sine or a cosine in them because you can start it like this. Now, some of you guys might be a little confused. Like, well, hold up. What about this 1 over x? How does that not change what these are on the outside? Nope, it doesn't. Because whatever you do to the inside of this function here only affects it horizontally. Doesn't affect it vertically. You guys remember that from transformational stuff? Anything done to the inside of a function affects it horizontally. Okay, moving it left and right, stretch and shrinking left and right, whatever. Doesn't affect the fact that it's between -1 and 1. That's still a true statement, and I can still start that way. Okay? So, knowing this fact then allows me to go one step further with it and say, okay, if that top statement is true, what if I take that middle and multiply it by x squared? Okay, well, think about like an equation. Whatever you do to one side of an equation, you got to do to the other. I've got a compound inequality happening here. I've got two inequality signs. Well, whatever I do to the middle of that, I have to do to the other two pieces as well. So if I'm going to multiply the middle by x squared, I got to multiply -1 and +1 by x squared as well. So now I've got my two functions that are trapped, or that it's trapped in between, -x squared and x squared. And I am hoping that if I take the limit of these two guys as x approaches 0, I get the same answer. Because if I do, whatever that answer is, it's the same for the one in the middle then. Okay? That's how that sandwich theorem is going to work. So let's check that then. So the limit as x approaches 0 of negative x squared. Can I do that limit? Remember, what's the first thing you always try? Can I plug in a 0? Be careful. Of course you can. Yeah, it's just 0, right? Negative 0 squared? 0. And limit as x goes to 0 of the other side, x squared? Also 0. So the function that's always above it comes out to 0. The function that's always below it comes out to 0. So based on that fact, both of these two limits equaled, in this case, 0. So therefore, the limit as x goes to 0 of f of x should equal, what? 0 as well. Yep, it's got to be the same thing. So this would be limit as x approaches 0 of x squared sine 1 over x equals 0. Okay, so let's real quick graph and take a look at that. Double check, make sure we're right, and then we'll be done. So back to our calculator here. So our function was x squared sine of 1 over x. And we're looking to see at 0, what is it approaching? Remember, it's not going to have a value there, right? If I try to put 0 right there, it doesn't work. But we're looking for the limit as x approaches 0. And it does appear to be doing that. Okay. And in fact, this function gets a lot more interesting if you make the window smaller. So, actually, is that right? Radian, yeah, okay. Let's see if I make this, let's just do this real quick. We're gonna have to make that even smaller. It's supposed to look all wavy, like I think it has to be like super small. Yeah, so it's kind of doing a little bit there when you get really, really small. You guys can kind of see that, right? Where that limit is. Okay, it's like coming kind of wavy-like in this way, wavy-like in that way. But it is approaching 0 from either side. Okay. Busy people. Okay. So I'm going to stop there. And then remember, tomorrow is your first online day, so you should have a self-assessment. There's a little website where you guys can practice with doing some limits, and they'll let you know if you get them right or wrong. And then there's a homework assignment, and then don't forget about the attendance.